Okay, let's get started. Any questions on previous material? Okay, how many of you do not have a lab group? Raise your hand if you do not have a lab group. Really high. Okay, that's a decent number. Okay, so I will plan to end lecture like a few minutes early, and you guys chat with each other and come up with lab groups amongst yourselves. Okay, take that time. Email the TAs. I sent out an email yesterday about it. And if you don't have a lab group, if you haven't self-organized, by the end of today, we'll just put you in a random group. And we're planning to keep the lab groups the same for all of the future labs, just to make the organization part of it a little easier. Okay, any questions on that? Logistics, labs, sign up for a lab time. Those are on Canvas. Okay, so the good news is we have a new document camera. There's no longer a black spot in the middle of the screen. The bad news is, according to the previous professor, it periodically just blacks out every 5 to 10 minutes. So we'll see if that happens. If so, I'll submit another request, try to get that fixed. Yes?
Have the videos been being uploaded?
They are on YouTube. I sent out a link. They're way too big to put on Canvas, so yeah. Yep. Let me know if you didn't get the email or can't find it. Okay, so we'll jump back into talking about convection. We kind of started on it a couple times in the past few lectures. So as a reminder, we're talking about convection heat transfer. So we've got heat transfer that is a combination of diffusion and advection. And so we have a solid surface here that is at a temperature Ts with a flow moving across it that is at velocity U infinity and temperature T infinity. And from fluids, you should be familiar with the fact that at a solid surface, you have zero velocity, and then the fluid forms a boundary layer as it moves across the surface. And eventually the fluid recovers to the kind of ambient flow velocity U infinity. The same thing is true with the thermal boundary layer. You have right at the surface, the fluid is temperature Ts, so the temperature of the surface, and then it kind of recovers up to the fluid temperature kind of further away from the boundary layer. And in this case, we have that the temperature of the surface is higher than the temperature of the flow, so we've got heat moving in this direction from the surface to the fluid, but it could be vice versa. So convective cooling or convective heating. Okay. So the velocity boundary layer, U as a function of y, and the thermal boundary layer, T as a function of y. So the thermal boundary layer can be greater than the velocity boundary layer, less than the velocity boundary layer, or equal to the velocity boundary layer. It just depends on kind of the setup and the circumstances of the problem. And we talked about having kind of the two different modes of heat transfer that are combined for convection. So near the surface, which mode do you think will dominate? Very close to the surface. So the velocity is low and the fluid is right next to the solid surface. So in that instance, you'll have more diffusion dominating. So heat transfer just by the collisions of the fluid and the solid particles. So at and near the surface, diffusion dominates. And then away from the surface, advection dominates. And if you remember from fluids as well, when you have a flow that's like just entering a pipe or just coming onto a flat plate, for instance, you have kind of an entry region where the boundary layer is starting to develop. And so when we get further into convection analysis, you'll have to determine, if we're in the entry region, if the boundary layer is fully developed, and all of that. So right now we'll just kind of talk about it conceptually. But, right, so away from the surface, advection dominates. And as the boundary layer grows, as the flow moves downstream, the heat that's transferred from diffusion into the boundary layer and then is transferred via advection up kind of into the main flow and carried downstream and up into the ambient air. So we'll say boundary layer dynamics are critical. And they really kind of determine how well or how poorly convection is occurring. So there are two main types of convection. The most common type that you might think of is forced convection. So that occurs when your bulk flow is caused by some external means. So some examples of that would be if you have a fan or a pump, or even atmospheric wind blowing over something. Some super easy examples of that are, like the cooling fan in your computer, just blowing air, forcing convection to occur and to cool the inside. The other main type is free convection. And free convection occurs because if you have a hot object, so you have a hot object just sitting on a table, the air near the object is going to warm up, and it's going to therefore have a lower density. The hot air is going to have a lower density than the air around it, so it's going to rise up just due to gravity. And as it rises, cooler air from the surrounding room is going to replace it. So that's going to create this kind of flow of air rising up and then cooler air coming in to replace it. So that's just basically buoyancy-driven flow. Let's see. You first. Buoyancy. And then it's driven by gravity. And if you think about, say you have an object that has free convection occurring, so you've got the flow moving this way, upward, due to gravity, and then you have a fan forcing air onto it in the downward direction. So in that case, the free and the forced convection would be operating kind of opposed to each other. You can also have them aligned. You can have the forced flow moving the same direction as the free flow, or perpendicular. So all three directions.
Can you have forced convection without free convection? Or is that just something we'll assume away just to simplify problems?
Yeah, so typically if you have forced convection, that's going to be way more dominant than the free convection. Right. So I guess if you have a fan that is blowing air over an object and it's kind of like moving new air in fast enough that you don't really have time for the air to heat up and like rise up due to buoyancy just from free convection, there would be like always, I guess, a tiny, tiny bit of that occurring. But typically, if you have forced convection, it is like so dominant that you just ignore the free convection component. Yes.
In like a situation where, like you described, like a hot object with like hot air moving upwards,
Yeah.
is the temperature differential between like the hot object and like the forced fluid over the, like if the forced fluid is not very cold, if it's kind of hot, right? Like, then, well, I'm trying to like work this out because then it's like a lot of it is still free. The force is not super effective, right? Like,
Yeah, so if you have, so we'll write down the convection rate equation in a second, and it depends on the temperature difference, right? The temperature difference between the object and the flow. So if those two temperatures are pretty similar, then you're not going to have conduction is not going to occur very quickly, right? So I think what you're trying to say, I think I get what you're trying to say, and if you are forcing flow over the object that's like pretty warm flow, then that's the flow that's going to be surrounding the object. Like even if the atmosphere is at a different temperature, the flow that's surrounding the object is going to be warmer. So then the free convection wouldn't occur very quickly either because you still have a very small temperature difference. So you're not going to have very much warming via like diffusion and then buoyancy either.
okay.
Does that answer your question? Kind of.
I think
Yeah.
it'll become more clear once we keep talking.
Okay. So these can be aligned, opposed, or perpendicular. Okay. So let's write down the convection rate equation, which we have kind of already seen when we were talking about our convection boundary condition. And this is called Newton's law of cooling, because everything is named after Newton and Fourier. So we talked about this previously. So we've got Q is negative HA times delta T, which is T2 minus T1. And then if we want to write it on a per area basis, so the flux, that's just dividing by the area. So remember, you'll often see T1 and T2, because this is convection, they refer to a surface, T sub S, and fluid, T infinity. Temperature. And again, we talked about this last time with our sign convention. The correspondence of each one. So the correspondence of T1 and T2 to Ts and T infinity depends on your sign convention. Okay, let's talk about this parameter H here. That is the convection heat transfer coefficient. So if you'll notice, take a look at this equation. It looks pretty similar to the conduction equation, right? Except we don't have a delta T on the bottom. So we have this H instead of K, and then we just have a delta T. Sorry, we don't have a delta X on the bottom. We just have a delta T, not divided by anything. So that's because, I think I mentioned last lecture, for conduction, you're often talking about, heat transfer going through a solid over a finite temperature or a finite distance, or even, an infinitesimally small distance. But for convection, you're really just concerned with the heat transfer that's occurring at the surface between a solid and a flow. So you're not really talking about any particular distance between the surface and the flow. So you just have the temperature difference, and then the area, and then this H is just kind of like a bulk catch-all coefficient that's often determined empirically, just to kind of say, okay, we know that for a given object that has a certain shape, whatever, we can kind of determine experimentally. We know that the heat transfer depends on the area and the temperature difference, and then we're just going to scale it with this H that depends on all these complicated things like the shape and the boundary layer and all the thermo properties and everything. So let's say H depends on what's going on in the boundary layer, which is determined by all these things like the shape geometry and the surface finish and everything like that. The nature of the fluid motion. And the kind of primary study of convection is typically focused on determining H for different situations. And I forgot to write down the units for it, but I think we can figure them out, right? So if the flux is, watts per meter squared, H, and then temperature is K, then you're just going to have the units of H are watts per meter squared K. So H is going to be different for forced and free convection, and as we mentioned, for forced convection, it's typically going to be much, much higher. So let's say H forced is higher than H free. And then you can have a fluid, a liquid or a gas flowing over a solid surface. And the H of the liquid is going to be larger than H of the gas, for the same reason that conduction is faster in a liquid, just because there's more molecules and they're packed closer together. Okay, any questions on convection kind of concepts? So for right now, we will be given H, and we'll primarily be using convection in combination with conduction problems. But a few chapters down the line, we'll get into how to actually determine H for like kind of given simple geometries. Okay. Let's move into this concept called thermal resistance. And this is really just a relabeling of something that we already know, but it's going to make it easier to kind of work complex combined problems with convection and then, conduction through composite materials. So a couple of days ago, we wrote down the heat diffusion equation for a plane wall with the with both surfaces held at kind of known temperatures. And for that, we got a temperature distribution. And let's write down all these assumptions that we made. 1D, steady state, no energy generation, isotropic, constant temperature, boundary conditions. And that gave us this temperature distribution. T of x is equal to T2 minus T1 over L x plus T1. So if we want to calculate the heat rate, the heat transfer rate, we can do that using Fourier's law. And we know we need dt over dx for that, right? We have t as a function of x, so we just take the derivative, and we get dt dx is the difference in temperatures over the length. So then q sub x is just negative ka T2 minus T1 over L. And let's rewrite that. Just distribute the negative and kind of pull out all the constants in front of the temperature difference. So if we look at this equation, it's going to tell us that this quantity right here, so kind of independent of whatever the temperature difference is, this quantity right here, if that quantity increases, then the conduction rate is going to increase, right? And that's kind of related to, so this is the thermal conductivity, and then these quantities are all kind of related to how well conduction occurs. So now, let's take the inverse of that, and we'll say if L over Ka increases, then what's going to happen? So now we've flipped it and said, if this quantity increases, then the heat transfer rate is going to decrease, right? Yeah, so that means that this quantity is decreasing. Its inverse is increasing. And this quantity, L over Ka, is the thermal resistance for conduction. So like I said, it's not really anything new. It's just kind of a new way of thinking about it, as far as this quantity is now, instead of how well is conduction occurring, it's kind of how is this material resisting conduction. So just taking the inverse of it. So RT conduction, the thermal resistance of conduction, is defined as T1 minus T2 over Qx. If you look up here, if you solve this for L over Ka, it's going to be T1 minus T2 over Qx, just rearranging the equation. So that's equal to L over Ka. Just different expressions for the thermal resistance. And it's helpful to write it this way because it's kind of showing that heat transfer is analogous to kind of the flow of electricity. So the flow of heat is analogous to the flow of electricity, and this thermal resistance is analogous to an electrical resistance. Okay. And you can kind of go through the same thing for convection, and the thermal resistance for convection is again T1 minus T2 over the heat transfer rate. And if you look back at the convection rate equation, you can see that that's just equal to 1 over HA. And again, here the T1 and the T2 are fluid and surface temperatures. So now we'll use this concept to analyze some kind of more complicated systems where we have convection and multiple types of materials. So we'll start with a plane wall with convection boundary conditions. Draw it nice and large. So we've got some flow on the left side that has a temperature T infinity 1 and a convection coefficient H1. And we're going to say this fluid is hot. And then on the other side, we've got flow that has temperature T infinity 2 and convection coefficient H2, and that's cold. And then we have our surface temperatures TS1, TS2. Define X in this direction. X1 equals 0 and X2 equals L. So knowing that much, we can already determine the direction of our heat transfer, right? It's going to be going from hot to cold, Q sub X. And then we can also draw kind of just a sketch of the temperature distribution in the system. So we know for convection, we're going to have the temperature equal to the fluid temperature out here. And then we're going to kind of come down to the surface temperature in this kind of boundary layer type, thermal boundary layer type shape. And then the temperature through the wall is going to be linear. And then we're going to come back out into the fluid temperature on the other side. And that's going to be our just kind of qualitative T of X.
Is there a reason why like it's shaped like that? Is that
Why?
Like a higher temperature here? Like,
Oh yes, yeah. So we're just looking at, for the problem we're just defining the X direction, but this is just saying like, okay, temperature is higher over here, so I'm drawing it higher up on the page, and then it's getting lower down on the page. Yeah. So you could draw like T. So remember we did this very similar problem with on the first homework with the composite, the double pane window. And based on that, say we're making all the same assumptions. Let's just list them up here. 1D, steady state, no energy generation, isotropic. It's important to keep those in mind because this concept and these equations that we're going to write down are for those assumptions. Okay. So we showed in the homework problem that the heat transfer rate is just going to be the same across all of these different areas or different surfaces. So we can write down this first convection problem. It's going to be equal to negative H1A. Remember T2 minus T1. So in this case, X is going in that direction. So we've got TS1 minus T infinity 1. And that is equal to the conduction through the wall. So the conduction equation, negative Ka, Ts2 minus Ts1 over the length L. And then convection on the other side, negative H2A times T infinity 2 minus Ts2. Yeah.
Wouldn't it be T infinity 1 minus TS1?
No, so remember we always are doing T2 minus T1, and we're defining our x's going in this direction. So this is like T1, 2, 3, 4. So if you're doing T2 minus 1, it's going to be TS1 minus T infinity 1. So T2 minus T1. Okay.
Sorry.
You're good. It's a little confusing when it's a convection one because there's not really like a distance defined. Yeah. Okay, if we just rearrange this a little bit, we're gonna distribute our negatives and then we're gonna take quantities that are in front of the temperature distributions down into the denominator. So T infinity 1 minus TS1 over 1 divided by H1A. That's equal to TS1 minus TS2. So now we're distributing the negative, so we're flipping the temperature. Divided by L over Ka. And that's equal to TS2 minus T infinity 2 over 1 divided by H2A. So all we've done is just rewritten these, distributed the negatives, and brought these quantities down into the denominator. So 1 over the quantity would just be the same as having it in the numerator. So we could go through the math here, just like you did in your homework, and show that you can express this as the, yes, question?
Just like in general, if you're doing this kind of a system, just computationally, could you look at the heat transfer flux instead and just like take out the area, and then if you want to figure it out for a particular area, just put it back in? I guess as far as just like the relationship between the flux and the flow, it's just per area.
Per area, yeah. So for Cartesian coordinates, for this type of thing, a plane wall, you could do that. The area is going to be the same for every term, and you could just look at this as a flux. But we'll talk about radial systems after this, and you have to be really careful there, right? Because as you're going out, the area, the surface area is getting larger. Yeah. So you can't cancel the area in that case. Okay. Okay, so like on the homework, we can just say Now, this is equivalent to, I'm not going to go through the algebra because you all did it on your homework, proved it to yourselves, right? But this is just equal to the total temperature difference which is the T infinity 1, just underneath the picture here so we can look at the picture. The total temperature difference, T infinity 1 minus T infinity 2. And notice here we're doing 1 minus 2 without the negative because we've distributed the negative through, over the sum of all of those things that were in the denominator, all of those resistances. H1A, 1 over H1A plus L over KA plus 1 over H2A. So this denominator here is the total resistance, R total, and that's equal to the sum of each of the individual thermal resistances of each component. And so just like when you have resistors in parallel, or sorry, resistors in series, you can add the resistances to get the total resistance. It's the same thing with thermal resistance. That's kind of the analogy there. Okay, I think we have time, if we're going to leave time to do lab groups, I think we have time to go through kind of one slightly more complicated example of this, and then we can write down the overall equation for that, and then call it good and get into radial systems next time. So this is known formally as a composite wall. And we're going to take what we just did, but make it slightly more complicated. Okay, so now we have 3 different materials, a wall made of 3 different materials. This is section A, B, C. It has thermal conductivity, 3 different thermal conductivities, K, A, B, and C, and 3 different lengths, L, A, B, and C. Again, we're going to define X as going to the right, and then we're going to have some fluid on the left. It is temperature T infinity 1. Its convection coefficient is H1. It's a hot fluid. Then on the other side, T infinity 4, H4, and it's cold. And then our surface temperatures are going to be TS1, T2, T3, and TS4. And we're just labeling these with S just to show that it's a surface boundary with convection. And then these are interior temperatures, T3, T2 and T3, and then TS4. And one way that is kind of helpful for getting started on writing down the entire equation for Q sub X is to draw this kind of little thermal circuit. So basically you have a node at each temperature, a resistor, and then a node at each temperature. This is bringing back like terrible flashbacks, like circuits flashbacks, right? It's okay, it's heat transfer. It's better. Let's see, I'm missing one. So now each node corresponds to one of the temperatures. So T infinity 1, TS1, T2, T3, TS4, and T infinity 4. And then you can write down the resistances of each of the kind of resistors. So the resistance of the convection and then each component of the conduction. So here going from T infinity 1 to TS1, that's happening via convection. So the resistance for that is going to be convection resistance, 1 over H1 times A. So that was our definition of the thermal resistance for convection. And then for the first bit of conduction, it is LA over KAA, LB over KBA, LC over KCA. And then the last one, again, is back to convection, 1 over H4A. So we've got a lot of A's floating around, but these big A's are just the area, remember. Distinct from this section labeled A. So if we wanted to write down the total equation for this, oh, and then you can draw, you know, kind of going into the circuit here is the heat transfer rate, Q sub x. So if we want to write down what Q sub x is, again, total temperature difference. So T infinity 1 minus T infinity 4. And then it's going to be over all of these terms added up, right? 1 over H1A plus LA over KAA plus LB over KBA. Same for C. And then convection. And you could do this for as many different kind of components as you wanted, right? We could add like 5 more different materials in there. Yes?
So in general, we're looking at temperatures further along the x direction as first. This kind of form, but in this case, it's opposite.
It's opposite because when we were first developing this equation, we just distributed the negative through.
Right. Oh,
So it's still consistent,
gotcha.
right? Because we started out by writing negative of T2 minus T1, then we distributed the negative through. Okay, yeah. So you can still get to this result if you start with the same sign convention that we've always mentioned. Okay. But if you just think about a setup where you have, okay, x is in this direction, then yeah, the equation is just going to come down to this temperature minus this temperature with no negative there. Yeah.
So the heat transfer through a wall is always going to be equal in and out? Like, is that
Given,
universal?
so that's why with these assumptions, yes.
Okay.
Yeah. So that's why I always try to emphasize.
Okay.
So I can write them down here too. So the composite wall, we're making the same assumptions here. So 1D heat transfer, steady state, no energy generation, isotropic. And those are the only conditions under which you can just kind of plug stuff into this equation.
Because I was just thinking, like, why would I ever start with the general form and pare it down?
Yeah, so in this class, these are assumptions that we make often, right? And usually you're going to end up with a much more simplified form where you can just kind of grab the simplified equation. But I want you to see that it's coming from kind of a much more general form that you could handle more complicated setups.
Yeah. Okay.
Yeah.
Cool, thanks.
Yep. Okay, any questions? Okay, so next time we'll start back in talking about cylindrical systems. And then the lab on Tuesday, we're going to meet in here and talk about it. It's going to involve some equations that I won't quite have gotten to in lecture yet. But if you're taking data on Tuesday, that's okay. You can still follow the lab handout, figure out what you need to do, and then we'll get to kind of the derivations of the equations that you'll be using later on in the week. And you'll still be able to complete the lab. So, if you don't have a lab group, take this time to form one. Thanks.